Hello everyone. Today I'm going to be presenting my research group's work on Zhuque. Failure is not an option, it's an exception. This work was performed in collaboration between the Non-Volatile Systems Laboratory at the University of California, San Diego, and the Architecture Research Group at the University of Colorado, Boulder. First, I'll give you a brief one-slide overview of our contributions. We developed a simple programming model for persistent memory systems which use flush-on-fail semantics like EADR or GPF. This model requires little or no effort from the application developer to use, typically no effort, and performs at least 3x faster on average than prior work, with flushes and fences removed to make it fair. Now that I've hopefully caught your attention, I will step back and provide some motivation and background for the work. So, as we're probably mostly aware, persistent memory is persistent across power failures, it is byte addressable, and it offers comparable latency and bandwidth to DRAM. So a naive approach to making a program persistent might be to simply take the program's memory and put it all in persistent memory. However, that doesn't really work because the cache has been volatile. So updates that are in the cache but not yet flushed will be lost if there's a power failure, and applications need to explicitly evict cache lines to the backing store for crash consistency. This has some significant consequences for performance and for usability. In terms of performance, the biggest issue is that explicit cache flushes amplify writes to persistent memory. You're going to end up writing to the backing store a lot more often if you have to explicitly evict lines after an update rather than waiting for hardware to evict them. Second, correctly placing cache flushes and the associated barriers is difficult. Many would say it requires expert knowledge, and it is quite a burden for the application developer if they want to make their program persistent. And third, the required memory barriers in multi-threaded programs also incur further overhead from pipeline stalls and synchronization overhead between coherence agents. So there's been a wide body of work created to make PMEM programming easier and faster. These works vary significantly in how they are implemented, but their programming models are mostly similar. They define a failure atomic section of where they divide the program's writes into sections, and after a failure, each section's writes are either entirely present in the persistent store or entirely absent. So we divided these works into 3 groups. I will discuss each of these based on their programming model, and I will discuss each of these 3 models now. The first and most common is the transactional model, which imports the traditional ACID transaction from database systems. So these either have an explicit transaction begin, transaction end interface, or they rely on the application's locks, since transactions have to match the locking semantics of the program. Or rather, transactions restrict the locking semantics of the program. And specifically, they restrict them such that lock, acquire, and release must nest perfectly, and the persistent memory can only be accessed when all the locks are held. Unfortunately, this prohibits common and useful locking patterns, such as hand-over-hand locking, which is where you're iterating over a pointer chain, and you lock the next item before releasing the previous one in order to ensure consistency. And this is a common pattern in multi-threaded graph applications that use fine-grained synchronization. So phases were created to address this limitation by relaxing the definition of the failure atomic section to the region between the first lock acquisition and the last lock release, not necessarily of the same lock. So this solves the programming model problem. It supports any locking scheme compatible with legacy applications. But in order to support this model, these generally require runtime tracking of dependencies between the threads, specifically read after write dependencies, because a thread can read an already written value and act on it and possibly end up in an inconsistent state if a failure occurs. Unfortunately, this runtime tracking incurs significant overheads in practice and can also lead to unrecoverable scenarios in adversarial cases, which we discuss further in the paper. The third model, which is sort of different from the others, is whole system persistence. And it's pretty much what it says on the box. Everywhere you would normally use DRAM in the system, you use PMEM instead. And the other big difference between the other models is there are no explicit cache flushes. The only time the caches are flushed is if a failure occurs, and they expect the system to deliver an interrupt in order to do this. So they used experimental hardware for this original paper about a decade ago. But in the past decade, manufacturers have indeed brought flush-on-fail support to commodity hardware in the form of GPF for CXL 2.0 devices and EADR for NVDIMM devices like Optane. These systems generally require the platforms to provide a guarantee that the caches will be flushed by a low-level firmware interrupt if a power failure occurs, and that there's enough power to flush the caches. So from our perspective, we would say this essentially gives us persistent caches. However, we still believe that the software model of whole system persistence is insufficient. First, it only preserves the contents of the application memory and provides it to them at restart. There's no well-defined model for recovery of the application. And second, we would say that the whole system does not really need to be persistent, and that introduces significant engineering challenges and probably some performance overhead. And but you're really probably only interested in making some specific user space applications persistent. So in order to address these criticisms, we developed a new programming model called whole process persistence. In this model, we transform all memory allocated by the process into persistent memory. If a power failure occurs, we deliver an operating system signal to the process after it is recovered. And execution simply continues from the point interrupted by failure. So this model has two main benefits over prior models. First, it is easy to use. There's no restrictions on locking or I/O, and our libc-based implementation is binary compatible with existing applications. Second, it's low overhead. There are no explicit cache flushes, and there are no write amplification from mechanisms such as logging or replication. So now I'll talk a little more about the design of our libc-based runtime and how it works. So at a high level, it's a modified version of libc, which implements the whole process persistence model. We chose to implement this in libc because libc provides the C bindings for Linux system calls and the threading API. And so that's where we interpose, we intercept, and transform the arguments to these calls to accomplish our goals. And it is entirely transparent to the application. We simply, all you have to do is set an environment variable and run your program as you usually would. So what happens when you run your program? During normal execution, we mostly modify ImpMap. So we return persistent memory for all anonymous ImpMap allocations. And we also return persistent memory for all private writable file mappings. That will be more esoteric things like your initialized globals in your program and your loader relocations. And the anonymous is your heap and your stack. And we also, since the kernel stack is volatile in our implementation, we would lose the user space context if a power failure occurs in kernel mode. So we also save that state, that context, to a separate PMEM region on every kernel entry. And we modified the kernel to do this. If a failure does occur, so as I mentioned before, we expect that the system will deliver an interrupt the application or the operating system to flush the caches. And we assume that this flushes the caches correctly. However, there's still the matter of the volatile architectural state, the register file, the floating point and vector unit context, and so on. On x86 at least, so the firmware interrupt that flushes the caches does save this state to memory. However, it's not to persistent memory. It is to some memory chosen by the device manufacturer. So to our understanding, it should be pretty straightforward to change this interrupt to save to persistent memory, but it is impossible to replace firmware on Intel systems without the platform manufacturer's cryptographic key, so we were unable to do that. Instead, for our evaluation, we simulated this process using user space signals, which push similar state on the stack, but would not be suitable for use in a real power failure scenario. So after a failure, when we restart the program, we have the virtual memory map and this volatile architectural state in hand. And so to restart execution of the program, we first restore the program's address space. And so that's remapping the persistent memory files we previously created. We restore operating system specific state. So we also track the state of threads and files and recreate them at restart. And finally, we restore the volatile architectural state. And since that includes the program counter and the stack pointer for each thread, restoring that is equivalent to restarting execution of the thread. At this point, if the application provides a failure handler, we run it before execution continues. And finally, I should note that there are some requirements for applications to use Zhuque. First is that threading file descriptors in virtual memory must be managed through the libc interfaces that we interpose on. Inline syscalls bypass those, and so will not work with us. And second is that applications must check error returns from system calls which interact with components beyond the process boundary. For instance, if a file system was not remounted after a restart, Zhuque cannot do anything about that. Now I will close with some performance results. So first, here are some comparisons of Zhuque on an older version of Memcached, which all comparison systems can run. The green bracket marks our improvement over prior work. As you can see, we moderate improvement and moderate overhead versus the native implementation. Zhuque is the red bar. As you may note, this version of Memcached doesn't really scale at all. It doesn't really gain any throughput from adding more threads. This is a known problem with early versions of Memcached, and later versions of Memcached were improved to fix this, including by adding fine-grained locking, incompatible with transactional schemes. However, that's not a problem for Zhuque. We can easily run that. And so we can run a much newer version of Memcached that is significantly faster than any prior version of persistent Memcached. Note that the y-axis on this figure is 5 times larger than the previous figure. And again, the green bar, so the black bar on these figures is Zhuque on old Memcached. And the orange bracket is our overhead versus native, which is also much lower than any previous persistent implementation, especially on the read-heavy benchmark. And finally, I will say that if the applications are less memory intensive, the picture is even better for us. So these are results from some selected benchmarks on the high performance benchmark suite. We ran the CPython interpreter on top of Zhuque and in native versions. And as you can see, we introduced minimal or no overheads in most cases. So, to summarize our contributions, we introduced a new programming model for flush-on-fail persistent memory systems and built and tested a libc-based prototype implementation. We found that Zhuque outperforms the state-of-the-art PMEM programming systems and can run a wider range of applications than prior work. And additionally, it's not on this slide, but we also provide formal arguments in the paper as to why prior systems are insufficient and fail to recover from some common scenarios. So, looking forward to your questions. Thanks for your time.